Hello everyone. Today's webinar is going to be on organic substrate selection and some factors to consider. This will be really focused on in-situ bioremediation. My name is Brad Elkins and I'm the Technical Sales Manager with EOS Remediation. Before we get started, I'd like to just introduce the company. So to start with, EOS Remediation, we're based out of Raleigh, North Carolina. We're actually the original developer of the emulsified oil technology for enhanced bioremediation. We hold patents for that technology both here in the United States and internationally. We're also globally recognized. Our products and reputation have been utilized on every single continent on the planet except for Antarctica. Something I'd like to bring everyone's attention to is EAS. It's our sulfate product for treating petroleum hydrocarbons mainly. And the exciting news is that we have been able to significantly reduce the price of that product. We wanted to be able to re-engineer, get better costs on some raw materials, and we want to pass all those savings on to you, the consumer. If you are interested in this product or would like information on how much we've dropped that price or would like to see a quote, please feel free to give me a call or an email. My contact information will be available at the end of the webinar. Also, we are introducing EOS 100, which is a new oil product, an electron donor product. It's 100% fermentable. It's a water mixable oil, and all you do to make it injectable is simply add water to it. It's really optimal for biobarriers, high velocity aquifers, and fractured bedrock aquifers. And it also received the PE Magazine's Editor's Choice Award for 2013, so we're extremely excited about that. So without further ado, I'll turn it over to today's presenter. It's Dr. Robert Borden, Principal Engineer with Solutions IES. Bob, take it away.
Thank you, Brad. I'm Bob Borden. I'm the instructor. I'm Principal Engineer at Solutions IES. I do soil and groundwater remediation work. Well, hopefully, if you're listening to this presentation, you all know what anaerobic bioremediation is, but I just put this slide up to remind everybody. Essentially, what we're going to do is we're going to distribute an electron donor. Typically, it's an organic substrate. That substrate will consume oxygen, it will stimulate microbial growth. But really, the primary thing we focus on is it ferments to hydrogen and acetate. And though the hydrogen and acetate is actually what's really used as the primary substrate for bacteria to degrade the contaminants. Just a list of some of the contaminants that the anaerobic bioremediation has been used to treat. Obviously, chlorinated solvents, but things like perchlorate, chromate, explosives, nitrate, radionuclides, as well as acid mine drainage. And I'm sure there's others, but just to sort of list them. For chlorinated Ethenes, I'm sure you're all familiar with the pathway, but essentially we start out with PCE. If you provide hydrogen as electron donor, there's bacteria that can convert that to TCE, releasing 1 mole of hydrochloric acid. TCE goes to DCE, DCE goes to vinyl chloride goes to ethene, and the net result would be you'd release, for each 1 mole of PCE, you'd release 1 mole of ethene and 4 moles of hydrochloric acid. There's a bunch of different substrates available: fatty acids, sugars, alcohols, emulsified vegetable oil. They all basically do the same thing. In most cases, none of the bacteria we're working with can actually use these as the primary substrate or the substrate they really use. The bacteria we're focusing on typically want to breathe or use either hydrogen or acetate, and all these primary substrates will ferment to hydrogen and acetate. But there are differences. Some ferment a little quicker, some slower, some because they're already more reduced, release more hydrogen and or release more or less acid. Some have trace nutrients. So there's a bunch of different, even though they're essentially all the same, there's some subtle differences. And that's what I'm really going to focus on in this presentation today, is try to point out to you what some of the differences are, why you should think about one versus another. I'm firmly convinced that there is no one substrate that's suitable for every site. Every site's a little bit different, and you just need to know the advantages and advantages, disadvantages is the wrong way to say it. The characteristics of the different substrates and how they affect the project, and to be able to pick the best substrate for your site. I presented some equations up there for fermentation. The top one at the top is lactic acid combining with water to release hydrogen, bicarbonate, and 3 protons. In reality, the reaction doesn't actually go this way. You don't go straight from lactic acid to hydrogen. You go from lactic acid to certain intermediates. Those intermediates eventually get fermented to hydrogen and acetate. But rather than mixing all that up, it's easier and a lot more convenient to just sort of assume everything goes to hydrogen or bicarbonate, so you can do apples and apples comparisons. What I've shown some simple examples there. What you do see, though, is even from very similar things, you can release more or less hydrogen, more or less acid, depending upon which substrate you use. So, like, for example, fermentation of lactic acid and sodium lactate is essentially identical. For each mole, we release 6 moles of hydrogen. But the big difference is, since lactic acid is essentially, or sodium lactate is essentially lactic acid that's been pre-neutralized with 1 mole of sodium hydroxide, you produce, 1 extra mole of sodium and 1 fewer mole of hydrogen. So sodium lactate is pre-neutralized lactic acid. Soybean oil tends to be more reduced. So, for example, here, for every 3 moles of carbon, you produce 6 moles of hydrogen, so a 2-to-1 ratio, versus for 56 moles of carbon in soybean oil, you'll make 156 moles of hydrogen. Soybean oil is a little more reduced, so you generate a little more hydrogen per pound or per mole. And that's sort of summarized in this table here, just comparing some of the things. And the other thing you have to remember is a lot of these different materials come, some of them come already diluted in water. So, for example, if you think you're buying 100% low sodium lactate, 100, quote, pure sodium lactate typically comes with, is actually about 60% sodium lactate, 40% water. So, if you work out hydrogen release per kilogram, sodium lactate has got about half the hydrogen per kilogram that lactic acid has, just because, the difference in molecular weight with sodium lactate as well as the higher water content. And just some of those things that, unless you think about them, they're not always completely obvious. If you want to look at it, that same results in graphical form, you can see, pretty dramatic differences depending upon the substrates. Soybean oil releases a lot of hydrogen per kilogram because it's so reduced, versus like something like sucrose. It's pretty cheap, but the actual hydrogen released per gram or kilogram is pretty low. Similarly, if you look at protons or acidity produced per mole of hydrogen, soybean oil actually looks like it releases very little acidity. Well, it's actually, the acidity is comparable, but since you produce so much hydrogen, the protons produced per hydrogen for soybean oil is quite low, comparable to sodium lactate. Ethyl lactate is, as an electron donor, is okay, but when you add ethyl lactate to water, it hydrolyzes, releasing ethanol and lactic acid, and so you get the acidity there plus the acidity of just doing the fermentation process. So there's, these are just things to think about. Not that, if you've got a well-buffered aquifer, you may not care about the amount of protons released, versus if you've got an acidic aquifer, this may be a big deal to you. just something to be aware of. You can also control the biodegradation rate of the compounds. Some compounds just simply ferment or quicker than others. We've tested a bunch of different materials, and you can see clearly, like here, some of these materials ferment very, very quickly, some of them ferment much more slowly, and by sort of judicious selection of the material, you can control that. Typically, the slowest materials to degrade are like paraffins or an extended release substrate that EOS Remediation includes in the EOS XR product. Hydrogen and soybean oil is a little bit faster, chitin's a little faster still, all the way you get down to here to alcohols and short chain fatty acids, and they ferment very, very quickly. If you want rapid degradation, that's great, but sometimes you might want to slow it down so you don't have to re-inject this frequently. One of the major products that EOS sells is emulsified vegetable oil, I thought I wanted to sort of give you a little tutorial again about how vegetable oil works. Pretty much all natural fats are triglycerides. That means, and I've got a picture here of soybean oil, but pretty much every natural fat is the same way. There's a glycerol core, and there's 3 long-chain fatty acids esterified to it. And whether it's lard or soybean oil or butter or whatever, it all looks like that. The only difference is the length of the long-chain fatty acids. It can vary from anywhere from like C12, typically up to C16, or probably the most commonly max would be C18. Now, the way this material degrades, bacteria come in and they cleave this linkage here between the glycerol and the long-chain fatty acid. And so basically what you end up with is a glycerol and 3 long-chain fatty acids floating around in water. Glycerol is really soluble, it's really easy to biodegrade, so that provides sort of a quick kickoff that you'll see. And then what will happen is the long-chain fatty acids, typically what happens is, the most common long-chain fatty acid you're probably familiar with is oleate. Sodium oleate is basically ivory soap. So if you take oleate, react it with calcium or iron or magnesium or sediment, basically the long-chain fatty acids precipitate out. And then since they're insoluble, they don't biodegrade very fast. And that's really one of the reasons why vegetable oils degrade so slowly. So the net result is you get this initial release of glycerol and then a much slower, steady release of hydrogen and acetate. And I just want to show you some data here. This is from a laboratory comb we did. We injected, EOS Pro into it. And you see here there's this initial pulse of high TOC. That's really glycerol that's coming out. And that'll last anywhere from 50 to 100 days. And then often what you see is a pretty rapid decline in concentration down to maybe the 10 to 40 milligram per liter range. But that 10 to 40 milligram per liter range can stay essentially steady state for years, because that's the long-chain fatty acids. They're absorbed to the soil. Essentially what happens is there'll always be 1% in the aqueous phase. That 1% ferments, it releases hydrogen or acetate. Once that long-chain fatty acid is removed, you get another one that releases, and another, and you get this sort of slow release from the sediment. There's a lot of people, when they do EOS injections, they see this big spike in TOC and they think that's great, and then the TOC drops down to 50 milligrams per liter, and they get worried that it's all gone. That's not true. There's still probably a bunch of long-chain fatty acids sorbed to the sediment. They're just being released slowly. That's the good thing about vegetable oil. That's the bad thing about vegetable oil. If you need really, really rapid degradation, since most of it's not in solution, you're not going to get really, really rapid release, and maybe you need to think about something else. But it's certainly something you need to think about in the process. The advantage of that slow release is you don't have to inject that often. Emulsified Oil Substrate, EOS Pro, I'm sure you're all familiar with it. I won't spend a whole lot of time on it, but it's basically emulsified soybean oil, small negatively charged droplets. The one thing I wanted to remind you is, at least for EOS Pro, they add some nutrients, basically amino acids, trace nutrients, and vitamins get added to the mixture to help the bacteria grow. What I want to show you is some microcosm results. This is actually courtesy of Paul Hatzinger at CBI. He did this actually a number of years ago. The graph actually says EOS on it. I think at the time there was only EOS. There wasn't a bunch of different varieties, but what actually got tested here was EOS Pro. He built microcosms to look at biodegradation of perchlorate and RDX for a whole bunch of different substrates. Killed a control with no added carbon, lactate, ethanol, hydrogen, crude soybean oil, Wesson, and EOS. I honestly was really surprised when I saw this, and it was a really pretty dramatic result here. EOS is basically soybean oil, lactate, and yeast extract. Well, and some vitamins and nutrients. The EOS mixture of all these materials worked much better than each of the individual components. And originally that was really surprising to me, but then you think about it, well, that's the same way with us. Humans don't live on just fat or just carbohydrate or just protein or just vitamins. They like a mixture of things for a balanced diet. Well, surprisingly, bacteria are not that different. It's not to say you can't grow the bacteria on just hydrogen and acetate. Certainly microbiologists can do that in certain cases, but that doesn't mean it's as easy or they grow as well. And so in some cases, when you have a challenging site, you may want to add some of these extra things to help things go a little bit better. The other thing to think about is this is just one metric, dollars per pound of hydrogen delivered. If you look here, look, EOS 100 looks great in terms of dollars per pound hydrogen delivered. But that's not to mean it's the best product for your site. And I want to point that out by an illustration. Some cases people use soluble substrate. You have to deliver the substrate to the treatment zone. If you can't deliver it, it's not going to work. For soluble substrates, people typically think that's pretty easy. You just inject it, kind of drifts over. But it really depends on the groundwater flow velocity. If you've got a high velocity site, either it's just naturally a high velocity or you're pumping water to generate a high velocity. Typically, soluble substrates are thought often to have a lifetime of maybe 1 to 2 months. If it's 2 months, 600 feet per year, you could get a transport up to 100 feet. And that, depending on your site, could work very, very well. But if you've got a lower velocity site, or, well, I'm not even sure 60 feet per year is low, and I tend to think that's kind of average, but if you're in this range and you're depending on transport by the natural groundwater flow, the soluble substrate may only go 10 feet. And so you need to build that in. That means you're going to have more wells, more injections, more everything else. Emulsified vegetable oil, it doesn't biodegrade nearly as fast. So transport is not really controlled so much by the biodegradation rate. It's controlled by oil droplet attachment to the sediments. And we know the amount of oil that attaches to the sediments is a function of a number of different parameters. One, silts and clays tend to have higher retention than like sands and gravels, but also depending upon the formulation of the material. EOS Pro, I spent a long time working on that. We worked really hard to get as low a retention as possible. so you could distribute a small amount of oil over a large area. EOS 100 has got a significantly higher retention. It's really targeted more to those sites where you need a lot of electron donor, just because you have a lot of electron acceptor, oxygen, nitrate, whatever, flushing in. So it's got a low, you produce a lot of hydrogen per dollar spent, but because of the higher retention, you need more to treat the same volume of aquifer. So for example, here I've got a table up here showing, sort of doing some comparisons here, and depending upon whether it's sand, silt, silty sand, or clay sand, you need more EOS 100 per cubic foot of aquifer than you do EOS Pro. And even though EOS Pro is cheaper, it still works out that, you need to inject more material at a somewhat higher price per cubic foot. So to treat a cubic foot of aquifer, you're going to have to spend more money with EOS 100. But since you've injected more, it'll probably last longer. So, depending on how long it lasts, EOS 100 might be cheaper, EOS Pro might be cheaper. It really depends on site conditions, and you need to figure that out. And that's what I'm going to show you in just a second here. So what we did is to try to illustrate some of the strengths and weaknesses of the different substrates. I went through, I used the ESTP Emulsified Oil Design Tool, and I don't say it here, but we also use the Soluble Substrate Design Tool, trying to look at life cycle costs for treatment of several different sites over a 20-year period. Obviously, if you can clean up your site in 3 years, then this may be very different. But we thought 20 years was a sort of reasonable time period for a lot of sites. We use consistent unit rates for all the alternatives, consistent design assumptions, so we're trying to compare apples to apples. Sand aquifer, a little bit of silt and clay. Assuming we're going to put a barrier in to cut off the plume. It's 200 feet wide. The injection zone is 10 to 40 feet below ground surface, and I've designed all the treatments for an 84% contact efficiency. That's a pretty good but not crazy high contact efficiency for a barrier. The groundwater velocity at the site is a half a foot per day, and I'm assuming I'm going to have a contact time of 60 days for EOS Pro and 60 days for EOS 100. Now, EOS XR has been designed to be more slowly biodegradable, so it'll last a long time. But then the thing you have to recognize is, if it's going to slowly biodegrade, you need a bigger contact time to account for that. Oil retention for EOS XR is pretty similar to Pro. EOS 100's got about double the oil retention in pounds per pound. And so if you take those numbers and you look inside it, what happens is, because EOS XR, you're spreading it over a 90-day contact time and a slower degradation, you only have to re-inject once every 12 years, versus EOS Pro, you have to re-inject once every 8 years and 100 once every 10 years. So if you just look at the initial costs, EOS Pro is the cheapest, EOS 100 is second cheapest, and XR is the highest, with substrate costs being a significant portion of the total, but not 100%. We've assumed a constant fixed cost for each injection, plus some labor. The labor here is a little bit higher just because we're spreading out over a bigger area and we need a few more wells. But now if you look at the 20-year life cycle cost, EOS Pro is the cheapest here. Similar here, but there's been a switch for EOS 100 versus XR. Over 20 years, XR is a little bit cheaper than 100 just because you don't have to re-inject as frequently. And I should say, I don't think I mentioned, I think all these costs are net present worth, and I don't remember that. I'm going to say I did it with a 5% rate of return on the investment. So, or it might have been 4%. They were all used the same rate of return, but I think it was 5%. Now that's, half a foot per day. I think that's kind of typical maybe. If you go to a high velocity aquifer, gravelly sand, 1.6 foot per day velocity, or essentially half a meter per day, things are moving much faster. I still use the same design contact times. Oil retentions in sandy, gravelly material are much lower, so you're not injecting as much to treat it. But the other thing is, a single injection doesn't last nearly as long. You're pumping a lot of water through that barrier, and you've retained less oil in the barrier, so it's not going to last as long. The initial injections look pretty similar, although the actual amount of substrate goes down a little bit. But now the 20-year cost, EOS 100 is quite a bit lower. Why? Well, because of the higher oil retention, you've injected more oil the first time. So you only have to inject once every 3.5 years versus every year and a half. So over 20 years, that actually saves you quite a bit of money on the substrate costs. Actually end up being the same. It's just since you have to re-inject less often, your labor cost is quite a bit lower. I don't want in any way pretend that this is a typical site or not a typical site. Like I say, every site's different. But it does sort of illustrate how you can, play around with the substrates you're using, select different ones to try to reduce your long-term costs. And, if you look at those comparisons, I don't know, maybe 1.4 million versus 2.3, 2.4 million. I mean, we're talking real money after a while. So it's probably worth the effort to try to really optimize your design. Use out into lower permeability zones. We can go back in, and we've actually gotten pretty good at cleaning up these transmissive zones. We can inject EOS in them. We'll degrade the stuff. But the problem is you can't really, we can't inject emulsified oil into clays, and unless you're willing to spend a lot of money for fracking or other things, it's just really very difficult to get good distribution and substrate into these low K zones. So what often happens is then, the stuff slowly diffuses out, and unless you've left substrate behind there to treat it, it's going to recontaminate the water supply. Now, there is a way to speed things up. One of the ways is to get higher contact efficiency. The more effectively you distribute the substrate, you're going to reduce the cleanup time. And there's a paper we did a few years ago where it looks at contact time for a source area treatment versus time to 95% mass removal. If you're, at least for these simulations, if you've got a 50 or 60% volumetric contact, you might be able to get 95% removal in a decade. But if you're only doing, 20 or 30%, you may be 50, 60 years. So getting higher contact can reduce your cleanup times, but it's not like it's going to get it to 1 year. It gets it to maybe a decade. So you're still going to need to maintain anaerobic conditions for a while. This is done with emulsified oil. Maybe people argue with me, but if you did it with a soluble substrate, it doesn't matter. It's distribution. If you can't get it in the clay, you're stuck with relatively long cleanup times. But that's one of the advantages of slow release substrates like emulsified oils. I took that same sort of information, we did life cycle costs, and instead of just having, I never know exactly how long it's going to take to clean up. So what I tried to do is just actually look at cost versus time to clean up. So we've got then similar site characteristics. I'm comparing soluble substrates, EOS Pro, and EOS XR. And I'm assuming, for a source area, we have to inject EOS Pro once every 5 years versus XR every 10 years. We actually think XR can do a little bit longer than that, but I thought that was a fairly conservative assumption. And you can see here, Well, if you clean up the site in 5 years, having a substrate that lasts 10 years doesn't do you any good at all. But if you've got a 10-year cleanup time, if you got a 10-year cleanup time, pumping soluble substrate in there every other month you're gonna go bankrupt. EOS Pro, it's significantly lower than soluble substrate, but if you use a very slowly degradable substrate like XR, you may be able to reduce those costs a little bit more. But that's really, it's so it shows XR is valuable, but really in a source area treatment. If you've got a high flux barrier like I showed before, XR is actually probably the worst alternative, because you need to treat such a large volume, and you really need actually a rapidly degrading substrate to sort of keep up with the process. There is no one perfect substrate. I'm firmly convinced. It depends on your site. There's a number of different factors: hydrogen release, acidity, complex versus simple, biodegradation, longevity, oil retention, obviously getting good contact efficiency, and then just all the other constraints of the site, how you inject it, how you move it around. Every site is different, and I guess I've become convinced that you can tailor the substrate to the site's probably overshooting. I don't know that we could ever do that. But certainly some substrates are going to be better suited, for a given site. One substrate may be better suited than another. And I think, actually, I think that's EOS's remediation strength, is that they understand this and can work with you to figure out the best approach. And I guess that's it.
Well, thank you very much, Bob. I'd like to first extend my appreciation for your time in educating us, and hopefully everyone found that very enjoyable. A few things I just wanted to remind the audience of is we will be at several conferences coming up this fall, starting with the Tanks Conference in Denver, followed by the Biennial Groundwater Conference in Sacramento, and then we'll sort of finish off the fall with the Florida Remediation Conference. So if you're at any of those, we will have booths, we'll have posters. Please feel free to stop by, and we'll be happy to chat with you about your site. Don't forget that we do, as Bob said, we do provide free one-on-one consultation and also free demonstration and training for you and your project team. If you need more information, if you want a copy of today's webinar or webinars from previous series, please visit our website. Look for the client login in the upper right-hand corner. If you haven't registered, please do so, and I would encourage you to use your company domain, not your personal one. And my contact information is below. Again, my name is Brad Elkins, and I will be happy to assist you guys however you need.